So I've been experimenting with some real-life samples, and I'm lucky to have samples which look interesting, kind of like SpongeBob pants on the triangular. Uh, so we have these two points, low points. Uh, so this is the data we have. So it is just it is just the plot of the source data, the first graphics, uh, and then we see how different learning algorithms render it. So we feed the source data to learning algorithm in order, for example, to do a guided parameter search. So when the learning algorithm can predict the points of on this graph that we don't have, uh, we can sample it for the points which might be interesting. Like what is the point here? High is the point here. So we might instead of sampling the real function, we can sample the learned model in order to speed up the search of optimal parameters. So this is an extreme learning machine. Uh, and interestingly, in this three-dimensional graph, we can see that extreme learning machines they have a kind of character. Uh, if I were to draw an analogy, I think it would be like throwing a blanket or throwing a sheet over the data, and this film blanket sheet kind of descends on the data and takes some kind of form. So usually this point where the sheet we kind of still holding the sheet, and we throwing it over the data, and uh, you kind of can sense that there is a surface that is uh, curved around the dataset. Surface that was modified to match the dataset. And also, a lot depends on the function. So, for example, if we will use sinus instead of some of some non-periodic function, if we use a periodic function such as a sinus, then this surface, this blanket, it is periodic. So we're throwing a periodic surface on the dataset, and it bends to match the dataset, but it remains periodic. So we'll try this now. So I switched the activation to sinus, and I'm disabling the JAX compilation because it wouldn't work with the math sinus because this is a uh, traced type. So this is not actually a number or array, but a traced uh, traced proxy of the data, and this proxy will not work with the usual mathematical function. So in order for it to work, we decided disabling the compilation. So it will take some time for this ELM to calculate. And by the way, this is a two-dimensional graphics of just the sample coordinates. Uh, Here is the ELM is slowly going through coordinates because here it's not compiled into machine code by the JAX. So this JAX it was compiled in the ELM to machine code, and now that we have disabled, this code is interpreted, and we see it is much slower because it's in Python. We should be able to generate this with some matrix operations. It would be different from the algorithm specified in the ELM paper because I haven't figured yet how to use matrix calculations to exactly match the ELM paper, but it should be okay because the specifics of how we generate the hidden layer output matrix, the specifics of it are not important because the hidden layers in extreme learning machine are used basically as a computational reservoir, computing. So the theory goes that the hidden layers are kind of reservoir computing for the extreme learning machine. So the specifics of how we make the hidden layer output matrix are not that important. So we should be able to calculate a simpler version of the hidden layer output matrix. So here we go. The extreme learning machine is trying to throw this blanket, the surface over the dataset, but the surface itself it is periodic because it is made of this periodic function sinus. So it matches the dataset somewhat, but it's a harder job for the ELM2, for the pseudo inverse in ELM2 to shape this surface to the dataset. And next, let's try rel. So seal is still there is some bending to seal. Whereas rel is straightforward, and we can see it in the surface usually. So here we are, and where I get this surface analogy is that there is usually a point from which uh, we see like bones. So it's actually like an umbrella surface which has some metal spikes in it. So it's like we're getting this spiked surface, and we're putting it over the data set. So it matches the data set somewhere, but the structure of the surface remains, and maybe like Batman wings, which have these spikes inside them as well. Uh, so it's kind of I didn't expect to have this character to have these kind of bonds in the learned function. Uh, it is an interesting side effect of using pseudo-inverse to learn, perhaps, and it might depend to a degree on how the pseudo-inverse implemented, I guess. So next we have uh, XGBoost, which learns by making a tree, and then learning a decision tree by applying increments to it. So it learns a simple tree first, then it learns a next branch of this tree, and then the next branch picking optimal splits incrementally. So it transforms the plants, the SpongeBob plants transforms into a simpler structure. So it kind of cuts off a certain dimension as irrelevant. Mm. And next we have a traditional classic multi-layered gradient descent, or more specifically other belief. It takes longer to train, so ELM and XGBoost are fast learning methods, and gradient descent is slower. So this one takes 31 epochs to train, and if we reduce the number of epochs, then we will get a different picture. So it matches the SpongeBob pants pretty well. But let's try it at a lesser number of iterations. Here I'm reducing this to just the 3,000 iterations, and we see that it kind of fails. So it reduces the error considerably. So it trains in these iterations. It trains, but we see that this training actually touches only a small portion of the surface. So the gradient descent it doesn't affect the entire surface right away. It works on some subset of it, which most contributes to the error, and only when it matches this piece of data, it starts to. So it's my hypothesis anyway. Maybe we can plot this learning process step by step and see how it gradually affects the surface. So ELM compiled to native code or vectorized works very fast and gives us some idea of what's going on, as well as XGBoost. So these fast methods can be used to approximate the dataset surface, approximate the dataset in order to guide the search of future samples. Other belief can be used as well, but it takes a bit longer. It depends on how much is the difference between the training this predictor and sampling. Well, actually, it's not that much. Training this other belief takes half a minute maybe. So the difference is not that big actually, and then we will be getting this smooth surface which might match the dataset better. So you see that the surface generated by a gradient descent, it's kind of similar to the extreme learning machine surface. So we still have this surface which is bent to match the dataset, but we have less spikes. So ELM is spiky with bonds, and I believe the surface is softer, so to speak. So this surface can into guide parameter search, and there are cases where guided parameter search is better, works better, finds interesting parameters faster than random sampling. And maybe we can use these learning algorithms interchangeably. I mean, one time we can train an ELM and use it to guide the sampling, and on another epoch, in another iteration, we can use the XGBoost or other boost. So we can combine several algorithms, sample from one from another, guide the sampling by one or by another. And what I wanted to do here is to compare how these traditional machine learning algorithms, extreme learning machine, I believe XGBoost, compare to Bayesian optimization used in the parameter search, or maybe to the tree-structured Poisson estimator, which is a implementation of this Bayesian optimization, kind of improvement of it. So I wanted to see if we have some samples whether we can make this predictive surface without Bayesian machine learning with simple traditional non-Bayesian machine learning, and I think we can to a certain degree use non-Bayesian models to guide the search. So if we adjust the learning rate, so the number of training epochs is the same, but the learning rate I have increased from 1 to 2, and it looks strikingly similar to XGBoost. So I believe with a small number of iterations, but larger learning rate, we can see that it's learning in this dimension. So it's kind of repeats the same simplification, which is very interesting. So it ignores any difference in this dimension and only learns in this dimension. Well, and if we give it some more epochs, it becomes a bit more like a surface, just a bit more like a surface, but it keeps learning in this single dimension mostly. So it's very interesting that the change in the learning rate it did not affect just the speed of the learning or the risk of hitting some numerical instability or maybe risk to remain in some local minimum. It changes the character. Like if I were to take a guess on the spot, maybe the larger step allowed the optimizer to recognize the benefit of learning on this dimension sooner, and so it has developed on this started to exploit this dimension instead of going both ways. And if we would keep the high learning rate, like 2 instead of 1, and bump up the number of iterations again, then we might see that the network has kind of overlearned. It made a wild guess. So I know from the dataset that there is no positive numbers here. So this spike from 0 to 1,000 and more than 1,000, it's a wild guess. So the network kind of decided that if we're going up, then this up might continue somewhere high. This is a blank spot. It's not in the training dataset. It's not in the testing dataset. But the more so it kind of explains how numerical instability happens. So while we are adjusting this surface to match the dataset, there is also something happens in the blank spots where the numbers. It's kind of a wild imagination because there is no training data. The numbers would run away at these points, and when they run away, they might hit the numerical instability, and the network will collapse. Will no longer compute. And it's interesting to compare the numbers. So usually when we train a neural network, we look at the error. And for example, when we train ELM and other boost, we know that after a number of iterations, other boost gradient descent will match the error better. We will get a smaller error. We'll match the minimized function better, and we'll produce a smaller error. It will fit finally onto the dataset. But it's one thing to see those numbers, like maybe error of 10 for other different error of 100 for ELM, and it's another thing to see that this error it looks like these bones or bars on the surface. It's connected to a kind of hard substructure that's hidden in the Sellinger's learning. And we see this hard substructure in XGBoost, but we see that the way to to feed this hard substructure is different between the ELM and XGBoost. So L kind of starts at one point, and XGBoost instead picks a parameter that is most relevant at a given step of the learning. So my point is that when we are training a neural network, we are usually not so lucky as to have just the two parameters and the output which can be rendered three-dimensional. We usually have a lot of parameters, lots of parameters, maybe hundreds or thousands, and representing them graphically is a separate problem. So usually we just look at the numbers, like maybe we make the graphics, but only graphics of how the error is reduced during the training, and that's all we look at. But it might be useful. Even if you have a lot of parameters in the input, it might be useful to pick one or two parameters and one output, and see a slice or a view of the learning on such graphics. Maybe we will glean some useful data from the slice, and maybe we can make a number of such slices. So instead of looking at just the error, we might sometimes benefit from looking at the character, at the surface of how the network fits the inputs. And it gives us some insight into the data itself. So we might call it exploratory data analysis, and also insight about network learning strategy.